Hi, we saw in the last video that it was possible to replace some quite messy calculus for a capacitor with simply 1 upon SC. In other words, everywhere we saw a capacitor, we could replace its generalized impedance, we could replace its AC resistance, if you like, with just putting 1 upon SC. What is S? Well, it's J omega, so it's 2 pi f times J, which is the complex number, but forget that, it's just a single symbol that we can manipulate. So we can have S plus S is 2S, S times S is S squared, and so on and so forth. It's just something which obeys the rules of algebra. So that's quite a nice representation, and that's equivalent to the impedance of a capacitor. Now, wouldn't it be nice if we could do something similar for an inductor? Well, an inductor, first of all, we need an equation to describe an inductor, and we have V of t is equal to L di by dt, and clearly that's in the time domain because it's got the t's there. Now what Laplace is doing is he's using a transform to go from the time domain to the frequency domain. You can also go from the frequency domain back to the time domain. Where did the maths come from? Well, obviously people have taken a large amount of time to work all this stuff out. There's only so much that we can explain inside here. Really all I'm trying to do is derive a simple expression that allows me to replace the equivalent impedance of an inductor in a circuit with something really simple rather than something messy like this, which I'm going to have a job manipulating inside any equations I develop. All will become clearer later. So in other words, what we're asking is what's the Laplace transform of a differential? Okay, we've got L in front here, but this is the bit we're interested in. This is the bit that we'd like to get rid of. Now Laplace tells us, and I'm going to come down here and put it in a cloud in a minute because that's what I did before, that g of t, which is any old function, just g of t, nothing to do with this at all, any old function which is equal to a differential, we can find the Laplace transform of that. And what that means that becomes is g of s, in other words the frequency domain, so this is time and this is frequency. What that becomes is s, and we're using f here, so that becomes f of s minus the initial conditions. Now we're not interested in the initial conditions, so actually we can get rid of that. So what that means is we have g of s is equal to s f of s. Well, this is what Laplace says, so put that in the cloud there. So that's how he tells us to go from a differential into the Laplace domain. So let's try and do this to here. So all we've really got to do, v of t must become v of s by the same reasoning. L, forget that for the time being. So di by dt must equal s I minus the initial conditions, which for this purposes of this we're going to ignore. But remember, we still have to multiply by the L. So where does that leave us? Well, v of s equals SIL. Let's tidy that up a bit. So what we have is v of s over, that should be I of s there by the way, v of s over I of s simply equal to SL. Now what is v upon I? Well, v upon I is the impedance, right? So that is so what that means is every time I see an inductor and I want to model the impedance of it, or I want to have a simple representation of it, So for a capacitor we have this is equivalent to 1 upon SC, and for an inductor is equivalent to S. So, job done, job done. So we have two representations of the impedance inside a circuit of these two complex objects, because what it means to be complex is that it's going to have a magnitude and a phase, but now we've got it down to this simple form here where we can take any circuit and analyze it. Okay, so if you're not very good at calculus or whatever, feel free to neglect all of this. Just suffice to say that Laplace tells us that for the resistance, I keep using that word for simplicity for the listeners, but the impedance for the inductor is simply SL, and the impedance for the capacitor is simply 1 upon SC. That's your magic block. With that knowledge, we could write a simulator inside a computer that could model any circuit we want, just with that knowledge. So you see how clever Mr. Laplace was when he came up with this simple conversion.